Let's say T is 10,000 and D is 1. And then here we are actually understanding with the probability of 36% that we are away from null by 0.01. So that's very big probability. So that's theoretical below power. You understand that?
Yeah. So if we have a large enough data, so like the two distribution will be very far away from each other.
That's true. So one distribution will be here at U, and then the other one will be at U. And he's infinity.
So the probability
Becomes one.
Yeah, one.
So let's make this was theoretical, right? Maybe let's do samples so that you understand it. Okay, so somehow it extends this discussion. That's very nice, right? So that you understand these concepts properly. And let's do the following. Theoretical but simulation with the phi of 0.5. So that's the blue curve. That's the blue curve. And then with the sample, which is, let's keep the sample with us, say it is 250. Alright. So let me just generate that. Now let's say number of simulations, let's say 1,000. And here I would say for S in a range of S. Okay. To make you really get the point and deviate from the theory to real data, I want to generate a sample and do testing. And by that I do the following. Theoretical power calculation. Rather simulation. So here I will generate xt equals mu doesn't matter. Let's have a mu. 1 plus 0.5 xt plus epsilon t. And then to db d 1 more 0. So that is what I want. I'm going to start with x0 being 0. Let's say the process will start from 0. And then we generate such processes. Or 1,000 different. So I want to test for each of them and then calculate the probability. So we reject and accept 1,000 times and then go. So here explicitly I will have mu to be 1. So I want to estimate basically this. So to estimate that, then let's actually do the following. Let's define a function AR1 simulation. See? And let's say it takes phi. It takes the sample size, and it takes the mean. Right? So here I would say x is a list. Right? And then I would say for t in range of t. X let's call x0 to be 0. So that's, where the process starts. And here I would say xt is equal to mu plus phi times x0 plus the short, which is 1 point of random or round of size 1. So that is good. So now afterwards we have x0, now that becomes the previous one. I will set it to xt, alright, and x will be appending to itself x. Okay. Do you see the logic? X0 is first 0. Now E is a random variable. That's a standard model. So xt, which is now, becomes mu plus p times the previous value plus the short. Now the previous value becomes updated, becomes a current value, and I collect the current value in this. So that's it. So, and then here I'm going to return x. So here then I would say x, which is the values that we estimate are AR1. Simulation of say phi is 0.5. Let t be 250. Let mu be 1. Now let's actually simulate 1, just to make sure that it's really working. Alright, so that's the capital X. Let's see this, 250 observations, and that looks nice. Alright. You're happy? Wait so that we start and we think. Like this will be the status for 1. Right, so that's the series. To estimate an AR model in Python, we need a package, or we have a package, that is from the stats models, the time series analysis section. There is a model which is called AR model, and then from that we import auto-rec. So that's an auto-regression. That's a big part of this stats models, let's see the orders. And you can use it to estimate AR models. So here we have an AR1. Where do you use it? So I activate that and then do it there. And so now if I want to estimate this, then I define a model which is the auto-rec of x suppose you have never estimated an AR model. That's right. So you have not estimated an AR model before.
Not with Python.
Not before.
Other,
Another part.
yes, like,
You have a here we have modeling of summary, and let's see what the details. And that is one thing. So that's the concept. It was wrong, right? That's we estimates 0.87, which is roughly 1. The confidence bands includes 1, so you don't reject the norm, and it is 1 for the 5%. And that's the AR coefficient, which was 0.5, and then this is what we estimate. Right? So that's sort of what we have. But now we have to do this in terms. So I will basically put this in a for loop for S in the range of capital S, which is 1,000.
Professor, like, we will have the pretty much samples are not exactly the same because we didn't set the same.
So again,
We don't have exactly the same result in the table. But pretty much similar because we don't have the same sequence.
yeah, because P is small. P is 250. Asymptotically we get 1, and asymptotically we get 0.5. Let's increase it and then see.
But I mean, like, I have
Different values.
they're really different X-ray.
Sure, maybe the C is the
Yeah, it should be same.
Well, but that's not an important
Yeah.
difference. You don't get the same thing. Let me do this. Alright, so just to answer me. That will take some time, doesn't matter. You understand that's what we do. Let's have it 10,000. So the sample size are increased to 10,000. 20,000. 1,000. Let's have it 10,000. Well, that becomes closer. And you remember that ARMA model, or less estimator for ARMA models, is not unbiased. We know that. Yeah? You knew this or not?
Can you say that again?
Yes. That's an important issue. So if you have, say, x equals this plus phi x t minus 1 plus epsilon t, and let's say we have the OLS estimator for phi hat. Expected value of phi hat will never be phi for small samples. So this is biased. This is not like OLS. OLS is simple sort of cross-section of if you had say yi equals alpha plus beta x I plus ui, then in your bachelor classes, then you learn that x is beta under OLS assumption is unbiased.
Yeah.
This is not the case with the ARMA models. That is how it is theoretical. I'm sure. If you don't believe me,
I just don't remember, but I know what happened.
this is bias.
Yes, okay.
And as such, then we want to analyze the behavior of the OLS estimator for the ARMA models. We never talk about the bias, rather we always show that this converges in probability to the true parameter. So we establish its consistency. It is consistent, but it is not biased. It means when the sample grows, this falls or that. But in the small samples, there will be a bias. The bias is a small, but it's not zero. Right? With the growing sample, it vanishes. Right? So that such, OLS estimator for ARMA models is consistent, not unbiased. And then you see the consistency. So you see, so increase the sample size, this gets closer and closer to the true parameter. There you see. So
Yeah.
yes. down to the process of doing the estimation. So, alright, so if I don't need the model summary, alright. Let's say I calculate the T stat. T stat. And what is the T stat? So the norm, so under the norm, the true parameter is 0.5. Alright, so as you see, so we have generated the data with an AR coefficient of 0.5. Alright, so that's sort of what we have. Now let's calculate the T stat. Testing whether phi is 0.5 against phi not 0.5. Right? So that's sort of what we have. So we write the T steps. So that's a loop that estimates or sort of generates the data, estimates the coefficients. Now we write the T steps. So then we have a numerator. The numerator is model of params dot log at location 1 minus 0.5 divided by the standard error. So the standard error, I think it is called BSC. Right, so yeah, so BSC. So these are the beta standard errors. Right, so stats model saves them in the BSC. Then this divides by the model dot BS standard error. Then we need an log at location 1. Right, so that is what we do. So now let's define a list where we will collect the rejections. Alright. So now reg. Basically append to it. Let's call it the reg is it? Alright, so now we say if APS, absolute value of the T stat, is bigger than 1.96, then the reg is 1. Reg is 0. So just write it explicitly, right? Don't make it compact. Alright, now look, here we have a rejection. If the absolute value of this is bigger than the critical value, then you reject, otherwise you don't. And then here this reg will be the collect, we collect all the rejections in this. So that will, I will append reg. Then I'm out of this, then I need the mean of what is range of range and PW. Mean of print. not a series. That's a single line. Okay. We don't need the Euler's. So now you're a file. Please don't run the program. You did?
No, I haven't. It has a
Take your time. So. I'm sorry, so just go on to your step.
Can you run?
No. I want to tell you what will this mean be. I want to ask you, not to tell you.
Okay. The meaning of this code.
And meaning, yes, but what will this return?
Meaning. So I think that
Sorry? So what will this be? The mean of this range?
what rejection rate?
Let's try. How much will it? Sorry? There are 1,000 regressions. Right? Regression 1 we run it. We reject or not. Right? So range, then we have here, will be a vector of, do we reject? Yes. Do we reject? No. Do we reject? No. Yes. 0. Or no. Then we look at the mean of this vector. And my question is, what do you expect? For this? There is a rejection mean.
Yes.
Zero.
Okay, 0.5. 0.5.
No.
I just feel like it should be there.
You're right. That's a very good feeling. Because we are under the node. And we reject only 5% of the times. So if you have 1,000 regressions, you expect in 5 of them to reject. 5% of them, which is 50. 50 out of 1,000 you will reject, the rest you won't. Right? So this should be 5%. That's the size. If it isn't, then it means you have a bad test. Right? If the test actually rejects more, then it is oversized. If it rejects less, then it is undersized. You need the size to be equal to the nominal value, which is 5%. Let's now run it. Hopefully,
So the
so that's the meaning of this meeting. This is the value. It's roughly 5%. So in 47 of all of these 1,000 regressions, we rejected the null. There were 1,000. In 47 of them, we rejected. The rest we accepted. Because the null is that the true value is 0.5. And we don't reject it too much. Only 5% of the times we reject it. Alright. You understood? Now this was the meaning of this code. Alright. Now let's say that the true value is
So I think because it's exactly like alpha is alpha, right? Because we choose that to be like 1.96, a little bit higher than the actual z. So like we reject
well, actually, no. This is not because of that. If I increase the number of samples from 250 to larger, so 10,000, and the number of simulations also more, then it will be right 5%. Well, that's an approximation. The approximation is not because of that is 1.9600, the fourth digit of this. It's not because of that. Alright? So this is because the sample is a small. Alright? So the estimator will not be so precise. And the number of simulations, well, that's 1,000, but that's sort of more about the sample size. Alright. Now let's do another thing. Well, the true parameter is 0.5. And then we test whether this is 0.55. Yeah? So you understood what it does? So here we have 0.5. That's the true parameter. And now I'm testing whether it is 55, which is wrong. And I'm under the old time, checking the old time. Right. So then what will the rejection rate be? As you said, that's a rejection rate. What do you expect for this? 5%, 10%, more than 5%, smaller than 5%, more than 5%. Because we are away from the true north. Let's run it. Well, that's 15.7. So there is roughly 16% chance that we understand that this node, that this is wrong. The probability that we understand that with this sample size is this. Alright? So now let's increase it by a little bit larger. For example, let's say 0.6. And we expect the power to grow, to be bigger, because we are shifting the distribution even further. Right? So we go further away from the node. So then the probability that we reject should be higher. And that is 0.5, like 50%. Right? So it's very high. If you remember the power curve, right? So the power curve looked like so it was in the beginning very loud, and then very soon was taking off. Right? So then I'm not so much away from the node, but then there is a little bit of a change, but afterwards then it was strongly taking off. Right? If you're too close, you don't understand it with a high probability. But then there is a region when you go away from it, then you understand. Right? Well, that's sort of what we have. I mean, that depends also on the sample size. And if I increase the sample size, let's say from 250 to 500. Right? Then the probability from 0.5 that we have it here should grow, should become bigger. And that will take a bit longer. That became 77. Why? Because the sample size grows, so the estimator is more precise. So the estimator becomes more precise. The standard error becomes smaller, then you have more sample. Right? Because the standard error becomes larger, then you understand with a higher probability that you are away from 0.6, 0.5. So the standard deviation became smaller because of the sample growth from 250 to 500. All of these concepts you know, of course, theoretically. Now I just did it like this. So let's have another break. We have so many breaks, come on. What is this in which you do? I need to go further and more and so on and so on. But you become tired. I don't become tired.